Hello everyone. In this section, we will learn about different discrete distributions, and they are really special cases of the binomial distribution. So I encourage the student to read this section in their own, but I will touch a little bit on the different distribution. So we're going to start with hypergeometric distribution, and let's look at this slide here. In hypergeometric, it's different than the binomial distribution in the following. The population is small. It's not large. So whatever item I pick from this population to this sample, it will impact the probability of the second item I pick, since the size in this population is small. So let's assume in this population, the total item n, item of interest r. So n minus r will be item of no interest. Now assume you are picking n items into this sample, and you want to find what is the probability that of this n item there will be x item of interest of type r. That could be item of interest success, item of interest could be amplifier of gain 10. So I can say in this sample there is x item of interest and n minus x items of no interest. Now, if I need to find the probability that x, the random variable x, equal, let's say maybe 5 or 10. So it will be the combination of interest. In this case, how many ways I can get x item from r items here. And that will be this combination. This is how many ways. And how many ways I can get n minus x item, this is the remaining items in this sample of no interest, out of n minus r items present in the population here. And that will give you this combination. Divided by the total possible way I can arrange a sample of size n coming from a population of size capital N. And this is this item here. And x, the number of items of interest, cannot be larger than n or r. It will be the smallest of both. I may pick up here 20 items, but item of interest in the population only 10. So x cannot exceed 10. And the minimum value for x, which is the maximum of 0 or r plus n minus n. And the combination, just a reminder, this is rx equal r factorial over x factorial times r minus x factorial. Now the mean of x, that items of interest in this sample, will be the proportion of items of interest. So then I can think of r over n as a probability of picking item of interest, multiplied by n, the size of the sample. So this will be the average number of x items of type of interest. And this will be the variance here. As I said, I'm not going to go through the proof. I'm just going to touch some application of it, and you can read the material in the section. So let's look at this example of 50 building in an industrial park. So we can think of the population n equal 50. 12 have electric code violations. So let's say the building of interest are the one with violations. So there are 12 of them. If 10 buildings are selected at random, so we selected 10 buildings. So here n little n is 10. What is the probability that exactly 3 of the 10 have code violations? So our little x here is 3. So we want to know what is the probability x equal 3. In this case, it will be, there are 12 of interest. How many ways we can select 3 out of these 12? Time. Building of no interest is n minus r. So that is 50 minus 12 is 28. And here, if n is 10, then building of no interest in the sample will be 10 minus 3, that's 7. How many ways I can choose 7 out of 28? This is how many ways. Divided by the total number of ways I can select 10 out of 50. And if you calculate these, you should get 0.27 0.03. What is the mean? Mu x equal. The proportion of interest is 12 over 50. So that would be 12 over 50 times the size of the sample, n, which is 10. So if I calculate these, I will get 2.4. So in this sample, the average of buildings with code violation, 2.4. If I calculate the variance of x, then I just follow these equations. And the variance of x will be n, there are 10 in the sample, r, there are 12, divided by the total 50 in the population, 1 minus r, there are 12, divided by 50, 50 minus 10 over 50 minus 1. And if you calculate these, you should get 1.489. We just talked about the hypergeometric. So now let's talk about the geometric distribution. And the geometric distribution, now the population is large. So the item I selected here, first, second, won't affect each other. So you can think of it as a Bernoulli trial. But X here that you are interested is how many times you will conduct the experiment, or you keep pulling items from this population until you get the first success. So you will just keep pulling until you get the item of interest. Or in communication, I will just keep transmitting until they receive the message. So X is the last item I will send until I receive a success. And that is the geometric random variable. So in this case, I will keep pulling until I get the success. Maybe the success will happen in the 10th trial. Then there will be here 10 minus 1, 9 failure, which is x minus 1 failure. And the xth item will be a success. In the population, I know the probability of success P. So if I want to know what is the probability that I will pick 10 or 20 until I get the first success, it's very simple. It's the probability of the success, because that will be the last item I pull, time 1 minus P, that's the probability of failure. And how many of them? X minus 1. If I have 10 samples, 9 will be failure and the last one will be success. So then that will be X minus 1. If I want to know how many times I will be sending or conducting the trial and I get the first success, it will be 1 over P, where P is the probability of success. So if the probability of success is 0.1, then probably I will be pulling 10 items until I get success. 1 over 0.1 is 10. The variance will be this one. That's the variation in the random variable x. And this is the geometric distribution. Instead of doing this example, let's do the following. Imagine you have here antenna in a poor area. The communication is very difficult, or the medium where you're transmitting is corrupted, and you are sending zeros and one. And the probability of success is 0.05. That means the receiver here will receive the signal not corrupted, and then transmission will be stopped. So the transmitter will keep sending the message until these receive it and stop. Now I want to know probability of x 20. That means I will be sending 19 transmission, error, and the 20th transmission, success, they receive it. What's that probability? Given that the probability of success is 0.05. Well, I have one success, so that would be 0.05 to the power. And I have 19 failure, so that's 0.95 to the 20 minus 1 is 19. And if I do this, 0.0189. And if I found the mean, what is the mean of x is just 1 over p. So that is 1 over 0.05. So this is 20. The negative binomial distribution is different than the geometric distribution in the following. Negative binomial, you actually keep drawing not until the first success, but maybe until the third success, then you stop. Or maybe until the rth success, then you stop. And now I want to find what is the probability that I will be transmitting, or the size of the sample x, until I get the rth success. And again, rth could be the third, the fourth, fifth, and the seventh success. So in this case, this is the negative binomial, and you need to pass r, third or the fifth or the seventh success, and the probability of success. The probability of x now, it will be the following. You kept drawing or conducting the experiment until you get the rth success. So there are r of them. R could be 3, so you conduct the experiment until you got third success. So r in the 3, so you have 3 of them, so that is the probability to the power of r. So you may be having 1, 0, 0, 0, 1, 0, 0, 0, 1, and then you stop. You got the third success. So you have 3 of success here, and the probability of success is p, so that will be p to the power of 3. And this is failure, 1 minus p, time another failure, 1 minus p, and so forth. So how many failure do you have? Well, you have x minus r. That's how many failure. X is the number of trial I did, or the size of the sample here. R is the number of success before you stop. And that will be the probability. Now, how many combination of these I have? See, I have 1, 0, 0, 0, 1. I may have 1, 1, 0, 0, 0, 0, 0, 1. So how many combination you will have? It will be, take the last item, because the last item is the success. So don't include it. So in this sample, you have x minus 1. And you have inside it r minus 1. Because I'm subtracting 1 from x because that's the success. I'm subtracting from r1 because that is the success. So it's not included in the combination. So then there are that many way you can arrange r minus 1 success out of x minus 1 items. And that will be the probability of each combination. And if I want to find the mean of x, instead of 1 over p, now it will be r over p. 1 over p, that was the geometric. Negative binomial, it will be 1 over p times r, because there are r success. And that will be the variance. So now let's take this example. Again, let's do the transmission. So sometimes when you transmit a packet, and this packet could consist of 8 bits, and you transmit it. And if there is one error in these 8 bits, maybe the computer or the receiver will be able to detect this error and correct it. Maybe if there is even 2 errors, 3, 4, 5, 6, 7, 8 bits. Maybe if there is 2 errors, then again, the coding mechanism, they call it channel coding, may be able at the receiver to detect these 2 errors and fix it. But if there is 3 errors, then that's it. It cannot fix it. So now the question is the following. You are transmitting these packets, and you will keep transmitting until the 3rd error arrives. Then you stop. Means something went wrong. And then retry again to retransmit. So now I want to know what is the probability if I transmit x20 packet. What's the probability that x will be 20 before I get the 3rd corruption? So what is the chance that I will be transmitting 20 packet and a 3rd error will happen and then I stop? So that will be the total of packet I sent 20 minus 1, because the last packet, that's where the error happened. So that's 20 minus 1. And I'm interested on a 3rd error. So that r minus 1, that will be 3 minus 1 time. There are 3 bits error. So that will be 0.013 of them. And bits with no error, 0.99. There are 20 minus 3, 17. So I'm using these equations. And if I calculate these, that will be 19 factorial divided by 2 factorial, 17 factorial, time 0.01, 0.99. And if you calculate this, you should get, so that's a very small probability. The final distribution in this section is multinomial random variable, and it's very similar to the binomial, except in binomial, in the population you have only two possibilities, success or failure. But with multinomial distribution, now the population may have many possible outcomes. So it could be x1, x2, all the way to xk. And this you can think of it as you are carrying out experiment, and the outcome of the experiment is not just two possibility. It could be 6 or 7 possibility. Like, for example, throwing the die. Now the outcome, there are 6 possible outcome. 1, 2, 3, 4, 5, or 6, the face value of the die. If we now take a sample or carry the experiment n time, and I want to know what is the probability in this sample n, or the outcome of the experiment that I carried out n time has outcome x1 that many time, has outcome x2 that many time, has outcome xk that many time. And if I add all these, I will get n, the number of items in the sample or the outcomes of the experiment I did. And each outcome here, x1 has a probability of occurrence. We call it P1 for the type of x1, P2 for the type of x2, and pk for the type of xk. So now I want to know, if I carry out the experiment n time, what's the probability I will get that many of x1, that many of x2, that many of xk? And the answer to this is this one. That is the probability, or the probability mass function of random variable x1, x2, x3 all the way to xk. If, for example, I have 3 x1 and x2 I have 4 and x3 I have 2, for example, then the probability of x1, which is this one, I will multiply it 3 times because I have 3 of them. So that is probability to the power of 3. Same thing here. If the probability of x2 occurrence is this one, then I will multiply it time px1, and this will be to the power of 4, and so forth. Now, how many ways I can arrange x1, x2, and x3? That will we use a combination. And we saw in chapter 2, it will be n factorial, the size of the sample, divided by x1 factorial, x2 factorial, all the way to xk factorial. And for multinomial, that is the simple, and the parameter you need is n, the size of the sample, and the probability of occurrence for each type in the population or outcome of the experiment. If there is only one possibility, success or failure, then it will be reduced to the binomial. Let's take an example. This you can read it in the textbook, so let's do this example. Alkaptonuria is a genetic disease that results in the lack of an enzyme necessary to break down homogenetic acid. Okay, some people are carrier of this disease, which means that they do not have the disease themselves, but they are carrier. But they can potentially transmit it to their offspring. According to the laws of genetic inheritance, an offspring, both of whose parents are carrier of this disease, has probability 0.25 of being unaffected, 0.5 of being carrier, and 0.25 of having the disease. So let's draw our population, and this is the probability unaffected, so that's U, and this is 0.25. So the symbol U is for unaffected, and probability for the carrier is 0.5. And the probability for the disease is 0.25. So that is the possible outcomes. Unaffected, carrier, disease with this probability. Now in a sample of 10 offspring, so the parents has 10 children, the parent are carrier of this disease. What is the probability that 3 are unaffected? So U, 3, unaffected. 5 are carrier, C the carrier, there are 5. And 2 have disease. and D is 2. We want to know what is the probability. So the probability U equal 3, C equal 5, D equal 2. So I'm not calling them x1, x2, x3. So that will be n factorial, which is 10, divided by 3 factorial, 5 factorial, 2 factorial. So this will give me the total number possible combination of 3 unaffected, 5 carrier, and 2 disease. Now each possibility or combination, probability of unaffected is 0.25. So that's 0.25. And how many of them? There are 3. Time the probability of carrier, 0.5. And how many of them? There are 5. Time the probability of disease, 0.25. And there are 2 of them. And if you calculate these, you should get 0.0769, which is this one. Now B, find the probability that exactly 4 of 10 offspring are unaffected. So they don't care about carrier and disease. They just want to know what's the probability that 4 of the 10 unaffected. So the other 6 could be all disease, could be all carrier, or 50-50. They don't care. Now you can reduce the multinomial to binomial. And I will think of the population this way. Unaffected is 0.25. Everything else, like disease and carrier, I will lump them as one group. And you can put DC here. And that probability will be the sum of these two, 0.75. Now of these n offspring, they are interested that x equal 4 or unaffected equal 4, and the rest we don't care. So now you can say this is success and the rest failure. And we can think of it as a binomial. So the probability U equal 4 equal 10. How many ways you can arrange 4 times the probability of unaffected, 0.25, and there are 4 of them, times the probability or the complement of unaffected, which is 0.75, and there are 6 of them. And if you carry these calculation, you will find the probability equal 0.146. So multinomial can be reduced to binomial if I am interested on one category, and the other 3-4 category I have no interest, so I can lump them as one category. So now I have only 2 possible categories, success and failure, and the multinomial will become binomial. All right, I will stop here, and in the next video we will talk about the normal distribution, which is also called the Gaussian distribution. Thank you for watching, and see you in the next video.